All right, we've settled on a production function for the economy. If we choose values less than 1 for alpha and beta, like this production function here, our function will exhibit diminishing marginal returns just like we wanted. We know that H represents human capital, which is our average level of education times our labor supply. We know how people get educations. We know how people are made. What we need to know now is how and why capital gets created. Remember, capital is the tools we use for production, things like shovels and factories and roads and computers and computer programs and stuff like that. So if we want more capital, we have to divert some of our resources towards making it. That means whatever resources we use to make capital can no longer be used to make goods and services for consumption. So capital is created by foregone consumption. If we think about this from the perspective of income, there are two things we can do with our money. We can purchase goods and services for consumption, or we can save our money for later. Where does that savings go? Well, as we will discuss in greater detail down the road, savings kept in banks is lent out to finance investment. And this makes sense. Whatever we're not spending on consumption now, we must be spending on the production of capital for consumption later. In the Solow model, all of our savings is turned into investment, and our income is generated through the production of output. That is, people will get paid when they sell the goods and services they produce. And so our income is determined by output, or Y. Thus, the amount of savings we will have will be the average savings rate for the economy, S, times output, Y. And that savings will become our total investment, or the total amount of new capital that is created. In other words, we will collectively as an economy save a fraction of our income, which will be used to finance the creation of new tools that we can use for future production. It's not all hunky-dory though. Capital wears down over time. Shovels break, factories need upkeep, roads get potholes, computers get dusty, and programs get buggy. This is what we call depreciation. And each year we will lose D times K worth of capital, where D is the depreciation rate. For example, we might lose 10% of our capital on average each year to this decay, which would mean our rate of depreciation is 10%. This gives us a theory of how the amount of capital we have each year will change. Since D is the fraction of capital we lose, 1 minus D is the fraction of capital we retain. So the capital stock this year will be equal to the quantity 1 minus D times the capital stock last year. If we have 100 units of capital and we lose 10% to depreciation, then we will have 90 left, or 0.9 times 100. But wait, that isn't necessarily all we have, because we might have created some new capital through investment. So our capital stock this year is actually what is left over after depreciation plus investment. And that sets us up for a special outcome. The economy will reach a steady state when the new capital created exactly replaces the capital lost to depreciation. That is, when the amount of capital we lose to depreciation, D times K, is equal to investment. Since investment is determined by our savings rate and income, we can rewrite the steady state as being where D times K is equal to S times Y. When this is the case, the economy won't be changing from year to year, because the amount of capital we will have will be staying exactly the same. Everything we lose will be replaced exactly. So how likely is this outcome? Very likely, in fact. And it will represent the equilibrium of our Solow model. Let's graph it and see why. Since what we have here is a theory about capital creation, we will plot our production function on a graph with output, or real GDP, on the vertical axis and the capital stock on the horizontal axis. Since these are the only two variables on the graph, it means we are holding all of the others, like labor, education, ideas, savings, and depreciation, constant. When we hold the other variables constant, our production function exhibits diminishing marginal returns for capital. And so we would draw it like this. This is our production function. Plug in the amount of capital, and it will tell you what real GDP will be. As we discussed, we will save a fraction of this output, which will be used for investment. That means the amount of investment will be determined by this line, which is just a fraction, S, of the production function. Lastly, we have the quantity of capital that will depreciate. This will be determined by D, the depreciation rate, times K. Since D is a constant, this will just be a straight line, like this. With each of these functions plotted out on our graph, we can think about what will happen at different levels of capital. Imagine that our capital stock was low. That means it is all the way over here on the left of our graph. The highest dot corresponds to the total amount of output, or real GDP, that we're going to produce with this quantity of capital. You can see it's pretty far down, not too good. But the second dot down represents the fraction of output that is being devoted to new capital. We're using something like half of our economy to produce new capital in this example. And the third dot down corresponds to the amount of capital that we are losing to depreciation. Notice that we are creating more new capital than is being lost to depreciation. This difference will be added to our capital, and so our amount of K is increasing, pushing us over to the right along the curves. At this new spot, real GDP is higher than before, and if we stick to our savings rate of 50% and devote half the economy to the creation of new capital, we will create more capital than is being lost to depreciation, adding more to our total capital again. This growth in capital and real GDP will continue until we reach this point, where those two lower dots converge. At this point, we are creating the same amount of capital as we lose to depreciation. So we don't add anything and move to the right, or lose anything and move to the left. We just stay right where we are. But say we get it a little wrong and create some new capital anyway. What then? Does it keep going up? Well, no. At this high amount of capital, the amount depreciated is higher than the amount produced. So we end up losing this depreciated capital for next year, shrinking our capital stock and moving us to the left along the curves until we hit the steady state again. And here lies the magic of the Solow model. With some simple assumptions, we now have a working toy version of the economy that tells us what we should expect to happen to real GDP over time. If you remember the puzzle about countries after World War II, this model explains it. Germany, France, Italy, Japan, and Austria all lost a lot of capital to the war. And so their economies saw a lot more capital creation than depreciation. But in the US, we had lost very little capital. And so we just remained close to our steady state without much room for change. This model is also an incredible tool for breaking down what factors lead to economic growth. For example, we can evaluate what happens when the savings rate increases. Do we get much economic growth? Well, if S increases, then it will shift the green curve, which represents our investment. More savings means more investment, and the whole thing will push upwards, representing a larger fraction of total output. This will move our steady state over to the right, and the economy will see growth in the capital stock and some corresponding increases in real GDP. However, because there are diminishing marginal returns to more capital, we don't see a very big increase in real GDP. There isn't much growth from higher savings. Back when Solow published his model, this was the big result. At the time, most people thought the Industrial Revolution and the growth that followed was the result of increases in capital due to more savings and investment. But Solow showed convincingly that such a change simply cannot explain the massive increase in economic growth over the past 250 years. Okay, let's reset and try another change. What happens when the depreciation rate decreases? A lower depreciation rate changes the slope of our red line, and it sort of rotates like this. Once again, we have a new steady state, a new point at which d times k is equal to s times y, which is over here to the right. Again, we see an increase in capital, but a pretty weak increase in real GDP. So this isn't a great source of economic growth either. Perhaps we need a change to one of our other factors, like education, labor, or ideas. Each of those, unlike S and D, plug into our production function, which will shift both the production function and investment. With a higher production function, whatever fraction we have for S will mean more investment. If we save 50% of our income and our income goes up, we're saving a larger quantity of money. So both shift up like that. And now we have a big change. The new steady state pushes up the capital stock just like the other changes. But now we get a huge increase in real GDP to go with it. This is where economic growth comes from. Human capital takes a lot of time and investment to acquire, so it isn't the best way to grow. Ideas and innovation are best, but they are both a lot bigger contributors to growth than savings or lower depreciation. This meshes with our understanding of the Industrial Revolution now, when economic growth was born, and it gives us a nice recipe for keeping it going. We need new ideas and innovations. So how do we get those?